So welcome back. Yeah, so last time sorry, I have to change my layout here a little bit. Last time we spoke about basically, great, now I closed Nuke. We spoke about the creation of the fluid dance guy, and also how to, mesh him and simulate it and render it and fade it and stuff. And then we also talked about the cloth setup here on the right. And Jörg, I found the confetti setup, so I can quickly show you the differences again. And then basically I'm open to whatever is most interesting to anyone. We can either talk about, the other setups like the sand guy, or the pyro guy, the RBD guy, or the plants growing, or even the fire setup. So yeah, I'm just gonna start with dot and cross products, because Dominic isn't here, but he thinks that it's the most important thing. It's the backbone of everything that we're doing. So to show how we can use it, or what is actually a cross product, you might ask yourself. Well, a cross product is basically if you have one vector and you have another vector, they basically form this invisible plane, right? And the cross product of these two would be basically the perpendicular vector to that imaginary plane. And to kind of show this, on this geometry, basically we have normals, right? So the normals basically look perpendicular to each face or to each primitive. And if we now basically create, we use the normals as an incoming vector, and we do a cross product of this and, for example, an up vector, which is basically just showing upwards, right? Then basically the resulting vector is, if we can bind export this. So let's call this the up vector. And then we can also create the results. So yeah, why not my normal? That's cool. And if I now display those and up. Good. So basically, this is a bit big. I think I did it here. Yeah. So this is an easy example when I'm using just a single point. Like this. And I set the normal to be basically in that direction. And if I now create an up vector, which is this this red one just facing up, then it creates this my normal vector, the cross product of those two, basically, which is perpendicular to the plane, to the imaginary plane that these two form. And the good thing about this is, so how do we put this into use, right? Well, for once, if we do a cross product with just an up vector and the incoming normals, then you basically get normals, or like a resulting vector that is following the surface quite nicely and creates those swirls, for example. So what we can then do is basically use this vector as a velocity, for example, and then put this into a popnet to create some particles. And then based on this popnet, I can create some sparks, for example. So now we have basically, crazy sparks that are following roughly the surface topology of our mesh. And there's also a thing called double cross product. So basically, if we cross again the cross product with the incoming normal, then we get something like this, where it's basically almost like a wind tunnel, and we can change the vector by just changing the up vector to something like maybe minus z. Yeah, and now it would basically be like, this kind of wind tunnel effect where it still follows the topology of the mesh, but depending on the incoming vector that I'm crossing it with. And then, so that's very quick overview about the cross product. And then the dot product, you might ask yourself, what is this used for? Basically, dot product is just comparing two vectors, and based on their differences, it spits out a float from 0 to 1. So again, if I look at the normal here, these normals look into z, right, plus z, and these normals look into minus z, roughly, these guys, for example. So if I create a constant vector, basically, as well, that is basically looking into plus z, so it's basically somewhere here, and I'm creating a dot product with the normal, and then binding this to the CD. I can also like bind this to another float. For example, test, I don't know. Then if we visualize test like so, and we maybe get rid of the color. I still get color for some reason. Maybe the viewport is frozen again. I think it's because of the shop. It's the material. Yes. So looking at test now, it basically, what it does, it creates almost like a shadow map, right? Because if I change this constant vector here in any direction, it basically compares the normal to the incoming vector. So currently, this vector points into z direction, right? So it checks, where are my normals looking? Like, they're looking here, right? They're also looking into z. So the comparison between that vector, the normal vector facing into that direction, and the vector that I'm dot producting it with is roughly the same. So the output is 1. And the more it basically diverges from the other vector, the smaller the value becomes. So basically, this is why this vector, which is facing in minus z, is basically black. And this can be used to, I don't know, generate stuff based on normals. So basically, now I isolated everything that is looking upwards, so I can scatter some snow here and pretend that I don't know, snow fell on this type of geometry. And yeah, that's basically a quick overview to dot and cross products. So nothing fancy. Cool. Then, because I kind of owe this to Jörg still, this is the confetti guy. So let's talk quickly about this guy. As you can see, it's also simming and rendering live in the viewport. I can almost, press play, and it basically would resolve almost in real time. And the only difference to what we had before is that the edge fracture, again, has a lot more pieces, 240. I think yesterday on the other example, we had like 40 or something. And it, again, switches on every third frame between this one. If we visualize this. So a lot of small cloth pieces, basically, and this one. And again, this gets then point deformed, and this is our source. I'm also changing the color randomly per point, as you can see. And this is basically then put into the exact same setup that we looked at yesterday. So the setups are, extremely similar. I'm also injecting high velocities in here. So if I look at the velocities in the very beginning on every 10th frame, I think, they're pretty high every 7th frame, roughly every 6th frame. And then they kind of get slowed down by the pop wind and the drag. And again, I'm doing the same trick as before, where I'm adding like a pop wind, like an ambient pop wind that has high velocities at the top and then almost no velocities at the bottom. Because if we dive inside, I'm multiplying it again, the amplitude of that force by py. So basically 0 at 0 and about 2 at the site. Cool. And this basically then gets fed into, again, Solaris, where I import the ground, the cloth, the camera that I made up, the lighting. I'm adding the materials as well, and then assign the materials. And yeah, there you have it. Basically, that's all. For everyone that didn't join yesterday, I recorded the session and put it online as well, so you can basically follow up about the creation of the other setups, because the other setups and this one are super similar. It's like 80% the same. Cool. Then, I mean, I do have maybe let's go back to the sheet. Either we talk about, growing plants, kind of like this, or kind of like this, or we could talk about the other dancing guys, basically. Not sure what is more of interest. So I still have the sand guy and the fire guy, which is the less interactive of all of them, because it takes a bit to simulate fire. But we talk about the growing plants.
Maybe plants.
Plants.
Yeah,
Okay.
yeah.
Oh,
Yeah.
a lot of people want to see plants. That's great.
Yeah, plants.
Yay. Okay. So I don't have the exact, setup that creates basically this output, but the technique is exactly the same. So there is just for completion's sake, there is an old method that is called copy stamping, and then there is a new method called for each. And when I initially created the setup, it was the copy stamping, and it has some performance down or upsides depending on what you're doing, but I'm mainly focusing on the new one because this one is old, as I said. Cool. So it all starts with a petal, so petal geometry, And I can do like a UV quick shades, which is basically it's actually a node that displays the layout of the UVs. So per default, it just creates a checkerboard. But you can use this as well to not use a checkerboard, but just like to preview materials or textures pretty quickly in the viewport. Then I can poly extrude it to give it some thickness, create normals. I'm editing the UV a tiny bit so that the petal basically is filling out the whole geometry, because I'm not using an alpha here. It's basically just pure geometry that's the texture scaled up. And then I am merging this together with a sphere, a tube, another tube, and together I get this pollen kind of thingy. I apply the same texture. This is going to be very, very small, so I don't really care if I have these holes here. So I merge this together, and now I have this weird looking petal. So now I can use, for example, bend stop to create a slide animation where it's basically folding from left to right. Just 2 keyframes. Then I do the same in the other direction. So basically now I have this unfolding of the petal. And then last but not least, I'm using, it's always the same deformer basically, the Z direction to opening it up like this. And so I have like this opening of a single petal. Then I scale it also over time, so it's a bit smaller in the beginning. And basically here then comes the important part. So basically what's happening is that I'm taking this animation. So basically I'm just treating this as a single animation cache. And then I'm time offsetting this based on when we talked about for each loops, there was this meta import node, and then that meta import node, there was like an iteration attribute, and that we used basically to create these variations in the buildings, for example, if you remember. And this is basically the same principle where I'm saying I'm time shifting this geometry, and then I'm adding basically the same attribute called, in this case, it's referencing this for each and for. And on that, there is an attribute called t offset for time offset. And yeah, long story short, if I'm doing this, and I basically, with this copy to points, I create this on a bunch of points here, then basically what is happening is that if I play this back, it takes the same animation, and then based on the rotation, which I'm specifying here, it's always the same principle. It's like on the Y rotation, I'm referencing this attribute called rotation offset, and it's also referencing the for each begin. And then the same for the translation, where I'm basically saying I'm offsetting every petal that gets copied slightly in Y. So this is why you have this offset. Basically, the first one that opens first is at the very bottom. The second one is a bit more on top, and then it's basically, yeah, you can procedurally generate an opening flower by just using for each loops and one single petal geometry, basically. Cool. So now that we have this, I'm also, transforming it back to the well, it has been in the origin, but I'm just slightly rotating it and scaling it down, and I'm merging in this little tube with a texture on it. And this is now basically my flower. So what I did here is basically, procedural modeling and animation kind of. So now this thing together with this and this, which is also just, the same thing that I'm doing over and over again, just with leaves. So the output of this one is this potato leaf that basically also opens up like this. And then I have another one. It's probably, I think this is a potato leaf, and the other one is like some other leaf. So I have basically these 3 assets that are animated. And basically what's then happening is I'm doing the same again. So what we saw here with the copy to points and all these parameters that are referencing attributes, I'm doing the same down here, where I'm basically creating a line that is growing over time. So if I play this back, it's basically just a line that is getting created. And based on this, I'm copying and time offsetting the plants again. And the more points the curve has, the more the slower it gets, kind of. So in the very beginning, it's kind of fast, like so. And you can see that in the very beginning, when the first points of this curves are born, so if I template the curve itself, it immediately starts to copy one of those assets that I define here at the very top. In this case, it's the not potato leaf. And it's basically saying on frame 1, on point 1, because this is point number 1 or point number 0, I want to immediately start the animation. So basically the time shift is my frame number plus 0, because 0 is basically my point number, right? So basically it starts right away at frame 1. For point 2 or point 1 or point 2 and point 3 and point 4, it's the current frame plus 1, 2, 3, 4, 5, 6, depending on what point it is. So this is not a simulation. It's just taking predefined animation caches and then time offsetting them and copying them on points that are point numbers that are increase in their number, and based on that number, they are basically time shifted in time. Since I didn't, so there is this option to basically speed this a little bit up by making it multi-threaded, and this is called compiling. I didn't do this here, so that's why it's a bit slow, but it's also a bit slow because I have a ton of stuff in the background running. So if I actually look at the copy stamp example here, I think this is actually even faster. Yeah, can, at least for visualization purposes, it's a bit quicker to render. But the principle is the same. The technique is just a bit different. Cool. So again, to go a bit more into detail, I am basically merging all of those assets together, and they all start at frame 1, so all at the same position. And then I basically create the name, or basically I promote the name from point level to detail level, and the promotion method is maximum. And I also changed the name from name to maximum. So what I'm ending up for is basically a name, and it basically takes the highest value of the name that it can find. And so then here, basically the same happens again, where I'm saying I want to time shift all of my caches that I created up here, and I'm saying it's basically my current frame number minus that iteration attribute divided by 3.5 minus a random variant of the same iteration attribute that I'm fitting between 4 and 10. So this might seem a bit abstract, but it's basically the same thing. It's like the iteration attribute you already know, and I'm just dividing this by 3.5 because this just looks good timing-wise when I copy back the animations to the curve. And then this minus fit random thingy is basically just, it's optional if I don't use this. Then, as you can see, some of the leaves are opening up a tiny bit faster than others because they're slightly time shifted with an offset of like 5 frames. So it's not like the first opens up first and then 1 frame after the next opens and then 1 frame after the next opens, but it's kind of like a variation to make it a bit more natural in a way. Cool. So yeah, this is basically the output of this. I'm unpacking it to have pure geometry. Again, creating normals, and I'm also getting rid of everything that I don't need anymore. So N, CD, and UV. And then I'm merging it together with the curve that it's used. So again, this is the curve that is growing, right? And I am polywiring this one and creating normals and give it a group so I can, after I merge it together with the rest of everything, I can still do material assignments because this is basically the group stems, as it says here. And I'm also time shifting this curve to the very last frame. This is also something that we do all the time. So whenever you have something that is growing over time, oftentimes we're time offsetting it to the last frame, so $fn. And then we create, for example, UV textures here, right? So maybe I can display them. Yeah, now it basically has UVs. And then I'm attribute transferring that back onto the growing geometry. So after my geometry is growing, you can see the UVs. I mean, it's not the best UVs on the planet, to be honest, but it's also like very, very thin. But the UVs stay kind of consistent over time. If I wouldn't do this, but just like give it UVs like this, then they would change per frame, as you can see here, because my geometry changes over time, right? So the projection method wouldn't work the same way. Cool. So again, I'm merging this together. So I have the growing plants. Yes. And then this is an optional second copy. So basically what I can do is I can use the same thing and time offset and point jitter it again. So basically I create multiple plants that are growing that are then copied together. So I end up with, not one strand of them, but many. I think I did this here on the right side as well, since this is a bit quicker. Well, it's not that quick either, but yeah, you can see it here with color at least as well. So I think in this example here, I think this is actually two plants together. But yeah, it doesn't really matter if you use this or this. Again, the left side is a bit more outdated, but still supported. And so now if we want to basically render this, right, what we have to make sure is, again, that we have UVs, of course, that we have groups so that we can basically separate the stem and the potato leaf, the non-potato leaf, and the flower. And as a matter of fact, I gave the geometries before I copied them. I created basically groups for them. So after the fact, I can even downstream here, I can later manipulate each of them individually or create shader assignments, for example. So to do this, we go into the stage context again. And you can see that this setup looks, again, quite similar to the setups that we looked at before. The only thing is that I now have multiple sources, right? I do have the flowers that I'm importing. I do have the leaves. I do have the other type of leaves, the ivy leaves, and the red ones, and the stem itself. So everything together basically creates this. And again, at this time in the node graph, I can't look through a camera because this gets merged in here. So first the lights come in. So if I look through the camera, if I'm here, and then switch to the Karma renderer on the XPU, then I can see I do get lights. This is without lighting, this is with lights, and this is with the camera as well. But I don't have materials, right? So I basically create them in my material library. They're pretty straightforward. Again, I'm using material X. And if I assign them and mix the lights up a little bit, you get something that looks a bit broken. Not sure why. And maybe that's also an interesting fact. The Karma XPU, it means that it's rendering on the CPU and the GPU, as said before multiple times. But what's interesting is that in the very beginning, you can see this optics stays on init. And so basically in the very beginning, it just renders on the CPU because it has the data already basically on the CPU, but it hasn't shuffled all the data to the GPU yet because that takes a bit more time. And as you might know, the RAM on the GPU is much smaller depending on which GPU you have. And so yeah, if it initializes and it's very slow in the beginning, the render, that's because it only renders on the CPU. And once the optics kicks in, basically once the GPU is used, then the speed increases exponentially, basically. Cool. So yeah, this is basically the outcome of the setup. And again, based on the curve that you're using, your input curve. In this case, it's just a circle that I'm resampling and jittering and create a little helix out of it, so that in the end it looks like this. But you can totally abuse this to even write with this, or let it crawl on some type of geometry. So I basically literally painted on this object basically, the curve, and let it grow. Because it's all procedural. So if you change, I can instance a rotating pig head, and then basically the rotating pig head would be instanced instead of a leaf. Not sure how this would look. I have to try it out. But yeah, you can just change all the inputs, being it the curve or being it the assets. Any questions about this? Nope. Cool. There's a text. All right. Cool. Is there anything else that we should talk about? Otherwise, I would probably talk about the sand guy, which is another vellum setup, like this one, or probably the RBD or the fire guy. Depends on what's more interesting. So here's a preview. Fire. All right. Let's talk about fire then. Cool. So this is the fire dude. Again, if we render it, you can see it's a bit heavier, on the heavier side. And this is probably a good example because, again, this is actually cached, but I'm doing, after the sim cache, a bunch of different operations, and you can see the optics here stays at 0%, and now the GPU kicked in, and now things are picking up. But in the very beginning, it's very noisy for quite some seconds, basically. And this is basically because it only renders on the CPU instead of the GPU. However, how do we get here? So it's actually good because we never talked about Pyro so far. So again, it's 80% the exact same setup as we had before. Again, it all starts with the animation, which is, again, our dancing guy. Yes, Ivona?
Screen is frozen or just moving. The first image.
Oh, yes, that's right. That is interesting. Let me...
No, thank you.
Is that back? Okay, yeah. Sorry. So then you actually didn't see the renders. So this is this is basically the output. And again, there's a lot happening post-sim, but now everything is noisy, right? Because the GPU doesn't render. And now the stuff, the image starts to resolve slowly because my graphics card has everything in RAM, and then it basically picks it up. Cool. And as you can see, this setup is fairly similar. Again, camera, lights. The only thing that changed is I have a couple of more inputs because I have the ground, the fire, another fire, sparks, a geo light, and the geo itself, the black geo, basically the holdout geo, and then the shaders and the shader assignment. But everything else is exactly the same again. Cool. So let's go through it. Again, it starts all with the same breakdancing animation that we've seen so many times by now. And here I'm doing everything just to show that, before on the other setups, we, if you remember, we did always like the source and then the sim. So basically we're prepping the source here, and then we are object merging it into the sim. But we don't necessarily have to do it. We can all do it in basically one go. So even if you just have one geo node, now I'm basically just prepping my source here, and then the simulation basically happens inside of this .NET. So it's, again, pretty free how someone wants to work. And yeah. So again, I'm object merging the guy. He is 125 meters high, so I'm giving him normals, making sure he has only integer frames, so no subframes. Then I'm blending it, so he again has subframes. So we can basically see if we now skip through this, and you can see here at the very bottom of the screen, that I'm skipping in 0.1 steps basically between the frames. So now he's kind of like slow-mo if I look at it like this. But just to prove that he is now subframes. And then I'm scaling him down so that he's 1 meter 80 or something. And then I'm giving him velocities as so many times before. So if you look at it, at the very first frame, he doesn't have any velocities because, again, this is set to backward difference. And in the 1 frame backwards, there is no frame. So I don't have any velocities. But then on all the other frames, I do have velocities. Cool. So to create a fire, we first, again, we need a source. So in Houdini, for a very long time, it has been actually that you convert your geometry into a volume and then use those volumes to drive the pyro simulations. And it's kind of still the case, but what they recently, like 3 years ago or so, did is they made it also based on points first. So I have my geometry, and then this points from volume basically creates a bunch of points inside of the volume. That's why it's called points from volume. So it's basically like a scatter node, but it's not scattering it on the surface only, but it scatters it inside a volume, basically. And I'm time shifting this to the first frame again, like we did in the last, I think the fluid guy or the confetti guy. I think the confetti guy was also time shifted to the first frame. And then we did a bunch of operations on this static frame. And then we retargeted this new geometry with the pointy form. So we're doing the exact same thing here. We have the geometry, and then we're basically time shifting this to the first frame. So now basically it's not moving anymore. And now I'm using this static mesh of points and pointiform it based on this one, which is the rest position, and this one, which is the animated one. So again, if I create a sphere, for example, and I position this weirdly somewhere where it doesn't make any sense, maybe at his hand or so. If I merge this in, it will still be retargeted by the pointiform, right? So again, pointiform is the coolest node on the planet because you can basically do a lot of stuff like retargeting without a rig, basically. Cool. So we are pointiforming this, and why are we doing this? Why don't we just use this instead? Because this is already animated, right? Well, as in the previous example, if we look at the point numbers, they randomly change because this is animated, and the points from volume basically fills on each new frame, basically the volume a little bit differently. So I don't have basically constant point numbers. And to avoid this, basically, I'm just doing it on a static frame, and then I'm pointiforming it. So now basically, if I look at my points, they basically stay consistent. Cool. So now I have a consistent number of points that are moving basically from what anim gave us. And I'm, again, time shifting this to the very first frame because this is my rest position. And this pyro source node, basically what it allows us to do is basically it takes the geometry to source from. So basically that's the first input, and the second input is the rest geometry. And again, rest geometry is needed to have basically always like an initial state for the Pyro source and the Pyro solver. And yeah, I'm also creating a REST attribute based on it. Cool. Basically, what this Pyro node does is it creates an attribute called temperature. So if we look at that attribute, it's basically just, you know, look at it here as well. Temperature. It basically is just a float that is set to 0. But what we can do now is basically in a wrangle, we can say, I want to take this temperature attribute, this float, so f at temperature, and I basically want to fit it from frame 1 to 24 to a value of 1.6 to 2.5. And I also created burn attribute that I set to 1. So this fit function, basically you can, fit an attribute that goes from, I don't know, 0 to 10. You can fit it to 0 to 1, for example, to normalize it. Or you can actually abuse the fit function a little bit and create procedural animation. Because if we look at our temperature attribute now, we can see that on frame 1, because we fit this attribute based on the frame, and we fit it from 1 to 24. So from 1 to 24, this temperature attribute increases its value. And basically this third and the fourth value that we're adding here between those parentheses define basically to what values am I fitting this. So on frame 1, it will be 1.6, and on frame 24, it will be 2.5. And that's exactly what's happening here. So we often use this technique to, create procedural keyframes. Because imagine you have an explosion, right? Or you have a shot where you have like 15 explosions, and you don't want to keyframe each explosion to go off at different times, right? You basically just want to give each explosion a value, the start frame basically. One starts at 1, second starts at 3, 5, 7, whatever. And all the forces that I'm injecting into each of those explosions, they sometimes need to be, animated, because in the beginning there is a lot of velocities, and then I'm reducing the velocities over time, for example. And I don't want to, keyframe all that for each explosion with each of the time offset stuff. So what we're doing is we can reference this based on a frame or a starting frame in that case, and have that basically update automatically. So on each explosion that I'm basically instancing, or not instancing, but placing and time offsetting, all the forces are getting updated live. Cool. Then based on this attribute that is called temperature and grows from 1.6 to 2.5 over the course of a second, I can also, use this and multiply this with a noise. So just to give it a bit more variation, so that it's not like, everywhere the same, because then it would look boring. And I'm doing the same for the burn attribute. So if we look at the burn attribute, it looks quite similar, but has a different, just a different seed. So it has just a bit of a different noise offset. Cool. Then I am creating a trail, and that trail I'm just abusing again to create a bit of a smeared source. So basically this is my original source and this is my smeared source, so that in very fast movements, I kind of have like almost like a motion blur, like geometry motion blur, like a fake motion blur, as you can see here. So the faster he moves, the more smeary he gets. And this is important because on the pyrosim, pyro is heavily dependent on the speed of the object that it's sourcing from. So if you have, for example, a rocket, and the rocket is like traveling at, I don't know, 200 kilometers an hour, then basically I'm creating a source here, and then the next frame, it's like 20 meters this way, right? So I have to kind of fill all these subframes with my volume. So this is why smearing this is one of the techniques that helps us to connect the missing space in between the two frames. Cool. So then I'm adding to my velocities. Well, first I'm creating velocities based on the deformation. So we've done this a million times by now, and this is working because I have a constant amount of points, right? If I wouldn't have that, then it would just go crazy. And then again, I'm adding just a curl noise to make it a bit more interesting, to break it a bit more up. And then I'm adding even more noise to this. And then finally, I prepped my source. So yesterday, when we were talking about water, we were saying that 80% of the work goes into the source, or a lot of the time goes into the source, because if your source looks interesting and has all the right values, then you don't have to do that much in the simulation. And this is especially true for Pyro, where you have to make sure that your burn and temperature attributes, they're not everywhere the same. They don't look uniform in any way, but they change their values globally, what we did here in the beginning, so it gets hotter over time. But then this is multiplied with another noise, and then there's a burn attribute with another seed of the same noise. And then I'm adding velocities, and even the velocities have a lot of breakups. So a rule of thumb is basically break up everything. Break up as much as you can to avoid any uniform looking CG look in your result. So, and I would say this is also the most common note that we get on first iterations of any effect. Can you please break it up a bit more? It's basically a lot of the time I'm looking at the sky and I'm seeing a cloud, and I would think, yeah, this cloud would get notes because it doesn't have any breakup and it looks very fake or low res basically, but that's how it is. Cool. So now basically we have these points with all these attributes. So, p-scale, burn, rest, temperature, velocities, all that kind of stuff. And now we volume rasterize this. So basically we are rasterizing those points into a volume. And we're rasterizing burn, temperature, and velocity. So basically if I middle mouse click on this, I can see that before I had points, right? And now I have 3 volumes, 3 VDBs, burn, temperature, and V. So burn and temperature are float volumes, and V is a vector volume because it has been a vector attribute as well beforehand. Again, here it's just points, and here it's then volumes. So this is my surface, but the name is a bit wrong because I just copied it over from the fluid guy. But this is basically out my source volume basically, but it doesn't really matter. So this I'm now feeding into a Pyro solver, and the Pyro solver is basically an HDA. So if we dive inside here, we can see there's a lot going on here, right? And somewhere here, there is our .NET. So this is basically the dynamics context that, previously we only had a couple of nodes in, but here we have like a bunch of nodes. And this is because they have all these switches, right? There's a switch here, there's a switch here, there's a switch here. So a lot of the stuff is not even used, but only if I tick it on. For example, if I say, I don't know, I want to limit my collision range, then somewhere inside of that node that we just looked at, there is a switching to the other input, because suddenly this group of nodes is then used inside. But this is why there's a lot of stuff happening that currently we don't even use. And the only thing that I added myself is I added a gas wind, which basically has a random wind scale based, again, on the frame. So it changes per frame and basically has some angulation on it. I added a gas vortex confinement, which basically, amplifies little eddies, little curls in the volume to give it more detail. And I did this twice with a different confinement scale. So big eddies and small eddies. You can think about it this way. And well, I cached this out because this took a while to sim. So this is basically the output of that simulation. And you can see the breakup that we added to the burn and the temperature, you can actually see, right? Especially in the first frames. There is like hot areas here. This is where the temperature and the burn was very high. And there is lower temperature values that we can see not that hot basically. And the same goes for the velocities. And this is why on certain frames, we have higher flames and we have flames that are not that high and all that kind of stuff. Any questions so far about this? Kind of jumping around a bit because of the time. I think, sorry, I have to check when is the next. Yeah, because at 4 p.m. I have another meeting. Cool, but this is basically the outcome of our fire. What I then basically do, there is this pyro bake volume, which basically just is can think of it as a post process where I can assign almost like a shader where I can say, do I want smoke or don't I want smoke? There is a scatter field which basically simulates the interactive light from the fire to the smoke. How bright is my fire? Do I need my fire at all? If I take this off, then it's just smoke. And yeah, basically this is all based on intensity scales, and we can also remap the ranges here to play around with the dynamic range of the fire and the attributes. Cool. Then there is a volume wrangle that basically just removes everything where the velocity is a bit falling under a certain threshold. So I'm basically multiplying the temperature everywhere to 0, where the length of my velocity falls below 1. And this basically, creates just a little bit of more breakup from the bottom where there's not much velocity. Then I'm sharpening the density. You can think of this almost as like a nuke when you do like a sharpen in nuke, but for volumes. And that is what basically then gets rendered. Currently, because I'm killing some temperature based on velocity, the viewport is not really sure anymore what he should display, because that's OpenGL. And yeah, basically this is going to be reworked with the Vulkan viewport now by side effects. But for now, we can kind of ignore that there is no fire. And what I'm then doing is I'm blasting the flame. No, I'm keeping the flame. And I'm converting this back to polygon. So this is something also quite interesting. Not can you only create from a geometry a volume, but you can also do the inverse. You can create from a volume a geometry as well. So in this case, I'm converting this based on this ISO value and adaptivity. I'm giving it normals and creating an attribute from volume, which basically is taking the flame attribute from the original volume and maps that onto the resulting geometry. And then this I can use to, based on this flame attribute, create a color on my geometry. And this is basically what we often export to lighting when we render our volume ourselves, but they need a volume for, interactive lighting for the environment or for characters or anything. Then we would basically give them this representation of the volume with some color attribute that they can shuffle into their emissive shader or geolight, basically, to light up the volume and the environment. And I'm doing the same as well. So I'm using this as a geolight in Solaris for final rendering. And that is it. There is also a secondary fire that I did that kind of looks like this. And this is basically, can go through it quickly, but don't want to take too much time. First, I'm creating a connectivity based on the class. So we end up with, that class attributes that is different for each connected piece. Create a bunch of attributes. And I'm randomly deleting, based on this class attribute, per frame, some parts of the body. And this is then piped into a vellum fluid. So basically, the output of this looks like so. Basically, I'm creating a quick little cheap fluid sim that is based on the incoming geometry that looks like this, right? So he basically, emits some fluid. And this fluid, I'm then taking to, run it through another pop sim. So everywhere where that lands, I'm injecting particles really quick. And if I merge all of this together and use this as a pyro source, so this is where it gets a bit maybe abstract again, but first I create a fluid sim, very cheap fluid sim because it's vellum. And then I'm using the output of that sim to drive a pop simulation, right? That basically is another type of simulation. And then the outcome of these two combined, I'm then using to create a pyro source. So basically, I'm just creating a pyro source again, and then, create a volume out of this at the end. So the output of these two simulations, I'm using to as a source for another pyro sim. So this is where you can see that sometimes we sim something and then we sim on top of that. And from that output, we are actually doing the main sim. And this is where it gets a bit tricky with the dependencies. So this is why there's like dependency graphs and stuff. So based on these points that, were based on a fluid sim, that are just like falling onto the ground, and whenever they hit the ground, there's another like burst happening. This is the resulting pyrosim. So you can see the moment it falls down to the ground, there is like this little whoosh effect, and it has velocities going upwards. This is because of the pop sim. And this then can be used to, doing the same thing, baking the volume, killing the slow temperature, and then sharpening up the density. So this and this can be merged together. This and this. So I end up with my main fire sim of just the guy burning, and then my secondary fire sim where, he throws basically like a Molotov cocktail, some fluid around that is burning and burning up the environment. Cool. And then last but not least, sparks. So what I did here is I used right before, I'm volume rasterizing the source points and they go into the pyrosim. I'm using a fraction of those points. So basically you saw that before. If a random number of my points go below a certain threshold, so in this case it's very, very slow, very, very low threshold, then delete all my points. So basically I have per frame different points but just a few of them. And this I feed into a pop simulation with some pop effect by volumes. And the pop effect by volumes is basically referencing this pyro solver here. And this pyro solver is not cached, but it's a very, very low-res version of my fire. So as you can see, this looks like shit, pardon my French, because it's extremely low-res, right? It's the same fire sim that you saw from the cache, but it's extremely low-res, but it's enough to create interesting-looking velocities that are following roughly the same structure as the high-res volume. So from this output, I'm just using the velocities, the velocity field of this output to generate on the fly without any cache, basically, particles. So the output of this basically looks, can just look at the cache here, looks like this, where we have a lot of, still a lot of points. I mean, just 1% of the original points that we can see here, but that's still a lot of sparks, basically. And these particles, we can then, make sparks out of it. This is another HDA that does a lot of things, but basically it spits out sparks. And then those sparks, we basically import as well to our render. So the setup is actually the only setup that does a lot more than the other setups, because it's not only doing, one source and one solver, but we actually have multiple outputs. Again, the secondary fire, the main fire, the geometry, the geolight, and also the sparks. And there's certain dependencies, right? From volumes from the fire to create the sparks, to create fluids, and then from that fluid another fire and stuff. But once we have all that, we have all the outputs, we can again go back into the stage and more or less, do the same as we did before. We import everything: the ground, the fire, secondary fire, the sparks, the geolight, and the holdout geometry that you can see here. We merge everything together. We merge our camera in. We merge our lights in that are dimmed down quite a bit. And then, in here, in the material library, I'm mainly using the pyro shader, basically. And I'm also binding some AOV for just a fire. So if I look at our AOV output, you can see that we have some AOVs that, more or less come for free already without setting up any custom AOVs. And yep, that is it. Again, it's a bit heavy because we have so many elements and then we have so many volumes, and volumes are always a bit tricky to render for every renderer. But as you can see, it's kind of manageable. And again, if you want to see it in motion, then it's this guy here at the bottom. And it's not the best fire sim in the world, but it's hopefully getting the point across. Cool. So we have 20 minutes left. Is there anything that wasn't clear from what I showed before, or should we, finish with the grain sim, with the sand sim? Then let's talk about the last one, or the RBD dance. So if you want to see like, the RBD guy, this guy, we can also talk about him. But honestly, I think the sand is more interesting. Cool. So let me open up the sand dance. Oh, this is 0 kilobytes big. This is not very big. Okay. So sentence 26 megabytes. That sounds better. Again, this is a bit more interactive again, because I don't have to cache a ton of stuff here. Let me go back to my view. Cool. So again, we start with
Screen still frozen.
sorry, thank you. We start with, you might have guessed it, with our FBX animation. We give it normals, we time shift it, we transform it. So now if you look through the camera, it makes sense. And now we're clustering it. So what this cluster node does, it's basically creating an attribute, not based on connectivity like the connectivity SOP, but basically randomly based on this number of clusters. So basically it created 40 clusters, 0 to 39 is 40, randomly on that geometry. And yeah, it's basically also changing per frame. And this is wanted in this case. And now I'm training it to compute the velocities as well. Sorry. So basically now, again, he has the velocities. And this I'm basically caching. Because the clustering is a bit memory intensive. So this is why I'm caching this directly to disk to keep everything nice and fast. So it still has the cluster attribute, as you can see here, and it's changing per frame more or less. Then I'm time blending this to again give it some subframes. I'm training this whole geometry a tiny bit, as you can see here. So it has like this double echo effect here happening again. I'm coloring it to give it just, based on P, different colors. And this is then basically my input for the grain constraint. So grain constraints basically just a Vellum constraint setup that basically says instead of creating points constraints between 2 points to create like a cloth sim or a soft body simulation, I'm just saying that every point is living on its own, is not connected specifically to any other point, and has a certain radius. And that radius is what makes it different to a pop simulation. Because on a pop simulation, the difference between a grain and a pop simulation is just that each point has a radius, and if another point collides with that radius, it preserves its own volume. Basically, it collides with the other point. So that's why in grain sims, things are stacking up over time, right? Again, if I look at this, at the very end, I have this big hill of sand here. This would never happen with a pop sim, because in a pop sim, it's just particles that have a p-scale, but they don't collide with each other. So everything just is like super flat and that's on top of each other. Cool. So we create these constraints, and the only thing that I did inside of here is, I think, created the particle scale, which basically defines how many points I have, because if I increase that, say by 2, then all the particles are basically bigger, but I also get less particles because they have less space, right? So this would be a very low res sim, and this one would be a very high res sim. That probably takes a while. So I went something in between where it looks okay-ish, but still is not too crazy. Then I'm attribute transferring my cluster attribute, because if I look at, again, clusters, I can see that these points, these grains that I just created, now have all the cluster attribute. Before, it lost that attribute when all this was happening. So to just regain that, I'm just transferring it back to the points that I just created. And then I'm creating an attribute called attraction weight. And if I look at this, it's basically a noise that I think ranges from, I don't know, up to 6, basically. I know that's just the amplitude. So it's an attribute from 0.1 to 1. And that basically is an attribute that gets used inside of the Vellum solver to basically say how weighty is my attraction towards each point. So basically each point will be clustered together to its neighbor based on that attribute. So wherever it's red here, I'm creating basically points that are trying to keep together as much as possible before a force or collision comes in that breaks them apart. And the higher that value, the more they stick together. For example, if you do snow, then snow has a very high attraction value, and yeah, you can basically noise that up like so. And this is also the reason why, if we zoom in here, you can kind of see this as well. We're getting all these clumps, like this travels together, and this travels together, and this travels together, all these clumps, because again, this is basically the noise pattern that you're seeing here. Cool. So this first is my input into my simulation, and then this is also my render output, because I'm basically merging the output of my simulation and my source together and render them together. But we can look at this later. And then the constraint itself, so not only the output of my geometry, which is the points, but also the constraints, I'm also creating an extra null for it. And so if I go back now to my simulation, to my .NET, you can see that it's my, again, pop object, pop solver, flip object, flip solver, Vellum object, Vellum solver. It's always the same, just different name. And then the source, I'm importing the geometry and then also the constraints. And the other thing that I did is like adding a ground plane and a gravity, and that's it. So again, since I spent not much time, but I spent some time on my source to make it interesting with cluster attributes and velocities that look interesting and stuff. I don't have to do much here in the .NET because my source already has all the attributes that make it look interesting. So this is not the fastest simulation on Earth, as you see, but again, you can see here it's actually a good example. The attraction weight attribute that we created creates these clumps, and you can see wherever there is a clump in the simulation, the attraction weight is 1 basically, and wherever there is no clumps, basically where we have free floating particles, this attraction weight is set to 0. So this is how you can pretty good see the influence that attraction weight attribute has. And I'm removing the normals. I'm setting a cusp angle It's basically just some render things that the render looks a bit better. And then in this Vellum post process, I think I'm doing absolutely nothing. It's basically just a preset. And then I'm cleaning everything that I don't need. So I'm cleaning everything. So asterisks, except my velocities, except my p-scale, and except my color, because these are the things that I need to for rendering purposes, right? So now I'm caching this out, and this is the result. So just a bunch of points, basically, that they kind of look interesting because of the attraction weight cluster attribute. And then I'm randomizing my p-scale. And I can't really display this yet, but basically it just gives every single point a slight variation in the p-scale attribute that is fairly small. So my global p-scale is set to 0.005, so extremely small, but it has a variation from 0.4 to 1. So basically 0.4 of 0.005 and 0.005. So if I now go to the stage context, you might look at something that, again, looks quite familiar, right? Because we are sub-importing our grain and the grain simmed. And this is basically what I meant before. This is my output of the sim, right? And this is my source that I'm injecting into the sim. Because my grain sim doesn't, like alone, doesn't really let me read the silhouette of the initial dancing guy. So I'm merging them together, and now the silhouette becomes a bit more apparent, right? So this is the output of the sim, this is my source, and together they basically, it's basically the output of the sim, but with a better readability on the source. And then I'm merging in my ground, as you've seen it a million times before by now. And if I render this to Karma, I can see that stuff like depth of field are already working. I'm adding my lights, adding my shaders. And yeah, there you have it. I think by now it's pretty clear. You know, I even didn't do anything fancy on shader level. I think it's really just a standard material for the grains, which is, you know, has this brownish color. And you can see the render is fairly slow. And this is because my graphic card didn't even pick it up. Now it basically picked up, and now it's actually fast. But before, it wasn't that fast because it was still putting everything into its frame. And yeah, you can see it's fairly detailed. So depending on my initial count of the sand source where we basically, the points from volume, created all these points, it's basically dependent on that. So from that scale, you know, from that far away, it's fairly okay. But of course, you need more sand particles the closer you are and stuff. But yeah, again, it renders with, you know, motion blur and depth of field more or less live. And the beauty again of this is that whenever we get a note now about, you know, can we please remove this guy? Then yes, I'm just selecting it, deleting it. Don't have to re-export everything. I just like press render and it's there again. That would be the benefits of using Houdini also as a renderer. But again, we're currently not doing it. And I should also say that everything that you see here, the, you know, nice little Karma render stuff that is fairly interactive, we don't even support pipeline-wise. So we can't even use this in Trickster or Cinecite at the moment. We're kind of fighting for it because it's just so revolutionary to work with this because it's so interactive. But currently, it's like, no, please use Mantra. And as I said in the very, very beginning, when we're talking about Houdini and its history. Mantra is like a renderer that's like 20 years old, 25 years old, and it's no comparison to this. Like it takes a lot longer to render something. Cool. So again, if we look at the overview, we I think discussed most of the stuff. We discussed how to create buildings and then cities, and then how to render them. Then we discussed how to grow plants. We discussed most of the setups, at least. You can probably by now imagine how the RBD setup looks like. It's basically a mixture of the confetti setup and the grain setup, more or less. Just with a different solver, with the RBD solver. And yeah, that basically wraps it up for the introduction to Houdini. Again, if anyone likes to, down the line in the future, have like a masterclass on anything, then I'm happy to do another presentation. But this is basically on a very, very high level, artist friendly, explained basically how stuff in Houdini works. Any questions? Yes, Jona.
Yeah, I wanted to ask, if I want to multiply, do I need to create a separate another setup, or I can just copy the one, for example, from the fire guy or sand simulation? Can I put two characters in one?
Yeah, of course. Yeah, you can.
Starting from the scratch, or
no, basically, actually we can do this on the fly. So if I, have this guy and then I'm transforming him, and I don't know, rotate him around 180 degrees. I don't know.
think the screen is frozen.
Sorry. Always forget that. It's just taking this one, transferring him, and then merging it together. So now I have basically two guys, right? I can totally use, and imagine this would be a separate animation, or like I can also do this with crowds, right? Everything would update more or less live. So in my .NET also, I basically now have two guys simulating at the same time. So it's, again, I can procedurally switch out the inputs and get a vastly different render out of it at the very end, as you can see here. Yes, and I can also combine it, I can combine confettis with fire and RBDs and sand, and that's where, yeah, it just gets very fun to work with as well. Yes, Jörg.
Are you going to share some of the examples with us?
Yes.
For sure, it will be good to try to build it from scratch again.
Mm-hmm.
And I think you presented it so well that I think it will be possible, but I'm sure we will get stuck at some point.
Yeah. Again, I'm going to upload all of those zip files. As it's just nodes, right? It's just basically nodes and positions and text and parameters. They're fairly lightweight, as you can see, like 20 megabytes or something. And luckily, the only data that you need is the breakdancing dude, which is also quite because of this guy. This one, the breakdance freezes, which is 2 megabytes, and the rest basically, as there is, most of the stuff is not cached, it comes for free. So yeah, I'm gonna upload them into the conference page where I upload all the videos as well.
Awesome. I think high-level introduction describes it pretty well. Thanks.
Exactly. No worries. Cool. Great. Then thanks everyone. I have to run to another meeting, so see you all soon.
Thank you. Bye.
Bye.
Bye.